All right, welcome to our talk. An overview of our work. We know that style transfer and inpainting are classic problems in image synthesis. And we showed that color palettes offer easy abstraction of color and structure in an image, which means that we can get better global and local control of image synthesis. So a key finding of this work is that weaker texture conditioning enables more extreme color transfers. And we find that diffusion models are very effective for dequantizing images. So if you look at the picture, the first column shows quantized images, so 4, 4, and 16 unique colors per image. And then the second column shows a prior work that does JPEG restoration, which is analogous to dequantization, but clearly not quite the same setting. And what that means is that a dedicated model for that task is required. So you can see in the third column, ours, we use a model that's designed for dequantization, does a pretty reasonable job of smoothing out the harsh boundaries and getting more lifelike colors. To quantize, we use the Python image library. All right, so let's look at our method. We use ControlNet to dequantize the image. And you can see here what a quantized versus ground truth image looks like. And for the conditioning, we'll go over that in a second, but basically it's going to look like the quantized image, an RGB image, and then optionally some texture information. So that's the extra channels. That's going to go through a trainable conditional encoder. And we have a frozen diffusion model. Our early experiments worked great on stable diffusion, but in this paper we used Deep Floyd Stage 2, which is a pixel space diffusion model. And so essentially the conditional encoder will add information to the activations of the decoder part of the diffusion model. And from noise, that's how we get a synthesized image. Let's look at our conditioning in detail. So the goal of the conditioning is to take into account the quantized image and then optional information about the quantization level and the texture information. So the first 3 channels are the RGB of the palette image. The fourth channel will be a single value representing the number of colors in the palette. Then we have 5th and 6th channels. So we actually trained 3 variants. First, we condition on luminance, and there's a kind of a long tradition of using luminance for doing any kind of color transfer work. The second option we try is conditioning on image gradients. So we take the image gradients in the X and Y direction and use that for the 5th and 6th channels. And then the third thing that we try is condition on thresholded absolute value of gradients. So we're basically reducing the amount of information significantly in the as compared with the normal gradients or the luminance. And we have a 7th channel, which is a binary indicator telling us is texture available or not at that pixel. Then we'll have kind of a 4th option as well, where we take our luminance model and we enforce the luminance, the source luminance as a post-process, where we convert to LAB space and then swap out the luminance channel. Our data set, we train on 1.8 million diverse images from Leon Aesthetic. And now let's look at a global color change. So this is at inference time. So we're going to extract a color palette from an existing image or use a pre-built color map. And to transfer the color, we'll use weighted bipartite matching. So this third column shows extracted palette from the second column. And then the first column shows the content image. That's the image we're trying to modify. You look at the fourth column, that's the result of applying the weighted bipartite matching, where we have a one-to-one correspondence between the source colors and the extracted palette. And then if we apply it, we get a quantized image. So these have 8 colors each. And you can see the remaining 5 columns, those are generated by our method, and they're in decreasing order of the strength of texture conditioning. So the first 2 columns, there's luminance conditioning, and you can see it didn't quite give us what we asked for because it added some blue to the kind of where this, I believe, egg yolk was. Gradient method, it has less of this issue, but still present. And then the threshold gradient and no texture, do the best job of kind of preserving the input that was asked for. And so that's kind of the key result here, is that people have been doing luminance for a long time, but you may be giving something up in the form of kind of the flexibility of what kind of colors you can make when doing a transfer. Okay, so we have another edit that we can do. This is a local color change. It's kind of like in painting, except in the region to in paint, we tell the model we actually want to preserve the source texture, but change the color. So you can see the mask and the color that was asked for in these three images. And in the bottom, you can see the synthesized result. So on the rightmost column, we asked for purple, we got purple. And to make these images, we use the gradient method, which is kind of in the middle of the strength of texture conditioning. So what that means is that it may not always hit the color that was asked for. It still tries to retain the source luminance. So it's kind of dark here. So it's going to struggle to make the yellow that was asked for. And then here's another example where we specify a mask and the color that we want, and then the result is harmonized quite well and adheres pretty closely to the color that was asked for. And then some training details. We only need 2 epochs to get good results for about 5 days of training on a single 840 GPU. And we train at 256 res, but at inference time, it supports a variable aspect ratio. And just kind of running vanilla inference, we get 3 seconds for 256 res image and up to a minute for a 2K image. But there's several things that we could do to make it faster in kind of a production environment. Okay, so let's look at some more results for dequantization without any texture conditioning. So here we can compare with existing works that also do JPEG restoration. On the left, you can see the quantization level, the number of colors in the palette. And the last column is the ground truth. And you can see the existing works, they struggle to kind of get lifelike colors. So for example, this woman's face, the existing images, they look kind of flat, whereas ours, they can kind of get kind of reasonable skin tones. So what that means is, again, we need a dedicated model to do dequantization, and kind of the existing JPEG restoration models are not enough. We quantitatively evaluate that our method can, so this setting on the left is without texture conditioning. It reconstructs images better than existing work, where we supply the quantized image as input, and then the output is the restored image. So we're doing a better job on our test set here. And on the right side with texture conditioning, we compare 4 of our models. So we compare texture conditioning, luminance conditioning, gradient conditioning. So here you can kind of see what we're giving up when we do our threshold gradient. When there's fewer colors, it may depart from the requested texture a little bit. You can see how the error metrics drop when there's fewer colors as compared with the other 3 options. So that you can see the trade-off here between kind of close adherence to the texture versus flexibility in getting the color that was asked for. And what we're saying here is that, you know, from an artist perspective, you should have all of these available to you. Here's a visualization again of the quantized image, what the luminance looks like, the gradient, and the threshold gradient. So threshold gradient is basically a binary image. The gradient actually has some pretty detailed information about the local shading. Some more qualitative examples. You can see, we take, for example, the first row, the content, image, style, extracted palette. What happens when you apply the palette to the content image? So these are, you know, the 4th column, these are the inputs to the network. These are quantized images. Then the remaining 5 columns are the output from our methods. And as you go from left to right, you get a weaker notion of texture, but you get closer adherence to the palette that was asked for. So the input is a palette that was asked for. And as you get less texture strength, you get closer adherence. And then a few more qualitative examples. I like this kind of coffee example, you look at the luminance conditioning and even the gradient conditioning, it's really different from what was asked for. But the threshold gradient is doing a pretty good job. And we can take color maps from any source. And so here are some synthesized results and a few more synthesized results. A quick summary of what we've done. We showed that diffusion models are highly capable of dequantizing images. We can use color palettes as an effective abstraction for image editing, like style transfer and inpainting, and thresholded gradients enable more robust palette transfers than luminance conditioning. Thank you so much for listening.